Now we are ready to say some special case of a linear map. Uh, what you have to remember is this one. Real number or complex number, they are just field k. But when you run vector space first time, we have told that R is R vector space. It is a real vector space. Or C is C vector space. C is also real vector space, but what I want to focus is that the fields are vector space on itself. So it means that you can define linear map phi some vector space V to C. Let us say V is K vector space. Sorry, then not C, I want to be general. K vector space. Then we can find that this is a linear map of this. Then, or we can write using the notation we learned before. We can write home VK. This phi has many names. It is quite important, but we are not going to tell detail. We'll just tell some basic thingy. It is called the linear map. It was a linear map, linear functional, or linear form, or one form, or covector, sometimes dual vector. They have many names, but it's all just saying that if you see these names, you have to think is that it is nothing, just a linear map, but whose target is scalar. So that is simple definition of them. Example is, of course, you can have zero map, which is 0 v to k, is that get every v and send it to just number 0. Other example I think interesting is integration, but not normal, it is definite integration. So you have some region. Let us define I v to k similar, but v is now some special case. V is some set of f. F is continuous real function. This is one of the simplest case I can think. TION. And then IF is calculated like this, 0 to 1 fx dx. Because this is number, you always get number. And we already learned that integration is a linear map. Definite integration is also linear map. I'll call later, but another example is that level surface, or just let us say just surface. When there is an arrow vector, you can make some surface on the space, let us say something like this. And for a given vector, you can always count how many surfaces are pierced by this arrow. This is 3, this is 4, and this is just number. So this is one graphical way to see the one form. So anyway, what you have to think is that, remember, is that it gets vector, its domain is vector, and domain is vector, its target is just scalar. Because this is quite special, this is special name called dual space. Sorry, set of these vectors home vk has special symbol. It is v star. Sometimes I prefer vv. So this is some special symbol for this home vk. This space, because it is also linear map, and we have learned just before last time that linear map also forms a vector space. So this is also a vector space called a dual vector space, or just a dual space. So if you have a V, you can always you can define some dual space, which is a vector space of a linear map sending the element of V to a scalar. And with this, you can have some spatial map. Let us write called dual map or dual basis. But let me explain first. Let us assume you have this guy, and this guy is basis for some vector space V. V is K vector space. Then you can define the set of map alpha I can be 1 to n, and alpha I ej to be delta ij. So this is just some defined map, and what I want to show is that this is also n vectors 1 to n, so number of alpha is n, and also basis of V is e1 to en. It means that this means that dim V is n. What I want to say is that alpha also forms a basis, but it is a basis for V star or VV. So basis of dual space. That is what I want to say. Okay, let's prove it. So this is what I want to say is that basis for dual space. What we want to do is that first let's write some f in VV. So what we want to find is that it spans the VV. So for all f, we want to say we want to say there is something like that fj alpha j if I forget to write f. If we can have a linear combination or spanning whole space j fj alpha j, if we can write every linear map one form with this form, then we can say alpha spans a dual space, and if we can also show they are linearly independent, then it is done. So let us assume some V in V. Then because E is a basis for V, we have a linear expansion I Vi Ei. Then Fv is F inside sum of I Vi Ei. But because it is a linear map, sum of I vi f ei. And also we have to see that then what is vi? Because v is if we set alpha I to v, then it is alpha I sum over j vj j ej, then sum over j vj alpha I ej, but it is nothing, just j vj delta ij, then it is vi. So this means that alpha I picks out vi. So using this, we can write fv as sum over I, and v was alpha I v f ei. And now what we have to do is that just changing the direction. It is sum over I and changing the order, ei alpha I v. And because the summation is on I, we can make some bracket together this, and comparing left and right side, we can say parenthesis v. Then remaining thing f is just this one. So what we show is that we have a linear combination. So it means it really alpha I spans vv. So this is what we show now. And the other is linear independence. It is also simple. So if let us check linearly independence. Linear independence is just the linear combination. Let us write v1 alpha 1 plus that. Let us write summation symbol. So if some c1 alpha ci alpha I is 0, this implies c1 c2 everything cn is 0, I 1 to n. Then if this is only true, if every ci are 0, then it is called linearly independent. And this zero map we already defined. Zero map is you get everything and everything are sent to 0. So it means that if you act some, especially, let us say this is some vector C, one from C. Just highlight this. Ci alpha I. Let us put some ej here. Then it is 0 ej. And this is ci delta I j and becomes cj and sum over I 1 to n. So it means that cj, and this is 0 map, so cj is 0. So this shows that if we put some ej, it shows that cj is 0. And we can do this for every j to 1 to n. It means that this means that this is true. So, and reverse direction is also true. So it is linearly independent. So we show that alpha spans vv and they are linearly independent. So we can conclude that alpha I is a basis for vv 1 to n. Because the number of bases is just n, we can also find that dim V is dim VB. This is also true. And this alpha is called dual basis. For E1 En. So if you have basis for V, then you can find some dual basis corresponding to it. And yeah, this is dual vector, dual basis. And also, the role of alpha was that if you go back, if you see this relation, the role of alpha is if you have alpha, you get some Vi. So role of alpha is just picking out the component. So it is in fact equivalent to just the coordinate functions, but we do not have any relation between two vectors. So what you can say is that for a given basis, you can pick out the component finally by the dual basis. So you can use one form, alpha I, to pick out the component, but you don't know EJ bases are orthogonal, because then you need to compare more than two vectors, because orthogonality is a relation between two vectors, or you cannot say the norm, so the size of basis, because you don't have any definition of length of the vector. So what you have here is that you don't have any structure. You just can pick out some component, the scalar, in front of a basis vector in the linear combination. So next time I'll go more on this.